Let's define a convex set geometrically. A set is convex if every line segment connecting any 2 points inside the set remains completely inside the set. Observe the blue shape. No matter how I move these 2 points, the yellow line connecting them never crosses the boundary. Now look at the red shape. If I pick points near the opening, the line passes through empty space. Because the line leaves the set, this shape is not convex. Consider a standard donut, a torus. If you pick 2 points on opposite sides of the hole and connect them with a straight line, does the line stay inside the dough? Is a donut a convex set? Pause the video and think about this. This geometric idea relates to algebra via convex combinations. Given 2 points, x and y, any point on the line segment between them is a weighted average. We define a point z using a parameter lambda, which ranges from 0 to 1. When lambda is 0, we are at y. As lambda increases to 1, the point slides along the line towards x. A convex combination of 3 points, x, y, z, forms a triangle. Can you visualize why? Any point inside the triangle can be written as a weighted average of the 3 corners. Pause the video and think about this. For convex functions, we have a powerful tool called Jensen's inequality. It states, the function of the average is less than or equal to the average of the function. Let's visualize this. Pick 2 points on the curve, x and y, and draw a chord connecting them. Pick a point in the middle. The red dot represents the function evaluated at the average. The green dot is the average of the 2 function values. Notice the red dot is below the green dot. The curve is below the chord. This gap confirms the function is convex. Another intuitive way to think about convex functions is the epigraph. The epigraph is simply the set of all points lying on or above the graph. Here is the key insight. A function is convex if and only if its epigraph is a convex set. Notice how the line connecting any 2 points in the shaded region stays in the shaded region. Imagine a 3D bowl. The space inside the bowl, the liquid capacity, is the epigraph. If the bowl is dented inwards at the bottom, is the space inside still a convex set? Pause the video and think about this. Finally, why do we care? In non-convex functions, like this red curve, optimization algorithms can get stuck in a local valley. But for a convex function, like this blue bowl, there is only one valley. Any local minimum is automatically the global minimum. This guarantees we find the best solution. What if our convex function has a sharp point, like the bottom of a V? Calculus fails here because there is no single tangent line. Instead, we use subgradients. Imagine balancing a plank of wood on the tip. Any angle that keeps the wood below the graph is a valid subgradient. It gives us a whole set of slopes to work with. This leads to the supporting hyperplane theorem. It says, for any convex set, you can pick a point on the boundary and slide a flat sheet of paper up against it without cutting inside. This plane divides the space into 2 halves. The set is entirely on one side. This geometric fact is the engine that makes duality work. How do we know if we found the best point in a constrained set? The first-order condition says, if you try to move towards any other valid point y, you would be going uphill against the negative gradient. We can simplify hard constraints using the Lagrangian. Think of physics. You want to minimize energy, like a ball falling down. The constraint is the floor stopping the ball. The Lagrange multiplier, lambda, is the normal force. It pushes back just enough to satisfy the constraint. Optimality is when these forces balance. The KKT conditions formalize this balance. Stationarity means the objective gradient and constraint gradient cancel out. Look at the arrows. The blue arrow wants to pull x to the left, to 0. The red arrow, the constraint, pushes back to the right. Complementary slackness tells us, if we aren't touching the wall, the force lambda must be 0. Usually, the dual problem gives us a lower bound. The primal solution is somewhere above it. The distance between them is the duality gap. Slater's condition is a technical check. It says, if the feasible set has an interior, meaning it's not completely flattened, then strong duality holds. When strong duality holds, the gap closes completely. The best lower bound equals the best upper bound. Solving the dual solves the primal. Finally, how do we solve these on a computer? Older methods, like simplex, crawled along the sharp edges of the polygon. It can be slow. Modern interior point methods are different. They define a central path that steers clear of the walls, surfing right through the middle of the set. As the algorithm runs, we lower the barrier parameter, guiding the point smoothly and efficiently to the optimal corner. Why is the interior point method often faster for huge problems? Think about a diamond shape in 100 dimensions. It has 2 to the power of 100 corners. Walking edges takes forever. Cutting through the middle is a shortcut.